Okay, so let's discuss diffraction and the uncertainty principle. So that's the title of this lecture: diffraction and the uncertainty principle. We're not going to discuss anything that we don't know yet, but we're going to discuss it in terms of the uncertainty principle. So the formula is that formula that we know from single slit diffraction is this. So that's the first dark fringe of the single slit diffraction pattern, and that theta means the angular size of the central peak, which is of central importance in the single slit diffraction. What I want you to focus is that the qualitative nature of this equation, which is that d sine theta is roughly lambda. So in this formula, it doesn't matter whether we have a rectangular slit, circular slit, or a slit that looks like a flower. It doesn't matter. D is the size of the slit, and d sine theta is on the order of lambda. That's the real content here. And so why is that? Why is this an uncertainty principle? In order to understand this, let's actually go back to ray optics problem, namely a geometrical optics problem involving a telescope observing a distant star, or an eye lens observing distant cars. In either situation, what you have is a lens, and this lens is used to image two distant objects. So two points here, two different stars, or maybe two different cars. So they are far away from the lens, and the light comes through this lens, and in this case the lens diameter is important, something that we never actually mentioned when we were doing geometrical optics, but now you will see that it becomes important. So now let's say that the image forms somewhere on the here is screen. The screen can be, focal point for the telescope situation, or could be back of your eye in the case when you are observing distant cars from an airplane. So anyway, so we got these two dots. So let's remember how we did things in the case of geometrical optics. So we always consider some sort of an arrow, right? So let's draw an arrow here. So we have an up arrow. We have a down arrow. A down arrow, I will draw it as a dotted arrow. And so what happens is that this object, the ray goes through this lens and go to the screen, and then it creates an arrow, and I'll draw an arrow shortly, and then this other object also goes through the lens, and then on the screen it'll form an image. So let's now draw the arrow here. So the up arrow becomes down arrow here, green one, maybe a little bit darker, and then here the dotted arrow. That dotted arrow appears. So in any case, so there's object A, object B, star A, star B, car B, something like that. So let's say this is A, B. The imaged dots of those screens. So that's it in the case of ray optics. And in that case, this angle is the same as that angle, and this. So let me note that this angle because the light is going through the center of thin lens, the angle's preserved, and this angle is also the same as this angle. So what this means is that if this angle is theta, the full angle is theta, the full angle is theta here too. And that's it. That's all we cared about in the case of ray optics. And when we discussed ray optics, did we ever know that there's this thing called diffraction or interference? No, we never cared about it because we didn't know better. But now we know better. What we do know is that when a plane wave, or it could be the spherical wave, doesn't matter. But in all examples that we did, we considered plane wave. So let's continue to think about plane wave. When a plane wave comes here and produces some output beam, if the plane wave that we care about is localized in the region of circular aperture where the diameter is d, then we know that that plane wave, right, that plane wave that comes into this circular aperture will actually diffract and produce an airy pattern, airy disk pattern there, where the disk size is given by this formula, right? So we know that. Having learned that, we can actually recognize, oh, here we have a similar issue with this distant star, plane wave, almost a plane wave, and this lens is just collecting light in a localized region in space in the form of a circle. And what is the difference between this, the effect of this circular lens and circular aperture as far as the diffraction is concerned? They're the same. What this means is the following. What this means is that when you observe the diffracted, when you observe the light here, in the geometrical optics, when we were using ray optics, we assumed that point A is mapped onto point A prime without any uncertainty in the angular position. But no. There is an angular uncertainty. What is the angular uncertainty? Remember, plane wave, which was zero angle, gets spread around the central position where the angular broadness, angular width is given by this formula, where the theta is basically half the angular width. So you can apply that to beams now which are coming in at a small angle in the same manner. So what happens is that the beam that comes to A prime is not a sharp spot anymore. It's a beam profile which actually, let me draw it this way. It's got a beam profile which has a blurred and the same here for the B prime. So I'm drawing these two beam profiles just so that the Rayleigh criterion is satisfied. So I'm drawing this in such a way that the half width of these angular profiles is exactly theta. Indeed, that's the Rayleigh condition. And we talked about this Rayleigh condition in the context of the grating physics. So the Rayleigh criterion is when two peaks when the two peaks are such that the maximum corresponds to minimum of the second peak, and the maximum, and vice versa, the two peaks are barely resolved, right? So then, in this context, think about this. The width here is the half width of this peak in terms of angle is given by this theta. So that's the Rayleigh condition. So that means d sine theta 1.22 lambda is basically the Rayleigh condition, because this angular separation theta agrees with the half width of the central peak, which is given by this equation here, d sine theta equals 1.22 lambda. When that happens, the two objects are barely resolved. So let's summarize. What we found is that this sine theta, and for the time being I will assume that the theta is a small angle, which is often the case. So then this theta becomes, well, I'm going to also drop 1.22 for this qualitative summary of what we found. So basically it's given by lambda over d. And what is the meaning of this? When you're using optical device of size d, this is your best angular resolution. Your angular resolution cannot be better than this. This is limit of angular resolution. And why is it limited? Because of diffraction, because of the wave nature of light. And this gives a fundamental uncertainty in angle introduced by your device. So then, what we should do is clear. If you want to have a super high resolution, then you need to make the device very big, and that's why, you know, if you look at telescope used in that's part of the reason why when you look at telescopes, the diameter is very big. Well, another reason is that if the diameter is big, then you get more intense light. But anyhow, the size of the optical device, the diameter of the optical lens that you use in astronomy has a direct implication of the angular resolution, namely how you can resolve distant features due to the diffraction physics. As the name implies, this uncertainty has much to do with the uncertainty principle in quantum mechanics. So let's briefly discuss that. So in order to see the connection between the angular resolution or angular uncertainty with quantum mechanics, let's consider this very well-defined problem here. Let's suppose that we found that at one point in space, the laser beam is a perfect cylindrical shape. Okay, so this could be laser beam right after it escaped a circular aperture. It doesn't matter how we prepare it. We're just saying that we just observe a circular, perfectly cylindrical laser beam of green light or something. And we know that this beam will diffract, right? Because, you know, this is all we need for the beam to show the Airy pattern, namely the condition for Airy pattern to appear on the screen far away is that at some point the beam has this cylindrical shape, either through a circular aperture or maybe not even. We don't care how it's prepared. As long as it looks like this, it will diffract the same way. Okay, so now we ask this question then. Why does this beam diffract? It might be actually it might seem actually a little bit strange to say that this beam diffracts, because all I said is for some reason we have prepared a perfectly cylindrical laser beam, and then I'm saying here that this beam should diffract, and you should convince yourself this beam should diffract according to what we learned so far. If you cannot convince yourself of that, then you have to go back to the theory of a single slit diffraction. And so we know that this beam diffracts because of the principle we call Huygens principle and things like that. But we will now formulate this in terms of some other principle, which is Heisenberg uncertainty principle. Heisenberg uncertainty principle is responsible for the diffraction of this beam as well. It's not surprising because quantum mechanics is wave mechanics, and so it's not surprising that the same phenomenon can be explained using different principles, which are all basically saying that light is a wave. Now, in order to explain this, let's consider this dimension d here, and let's consider x, y-axis here. Let's consider the y-axis only for the time being. So, what does the uncertainty principle by Heisenberg tell us? It says delta y, delta py is greater than or equal to h bar. When you learn quantum mechanics, you'll be able to learn to write down this this inequality in a more specific way. But here, for this discussion, we're actually doing a qualitative discussion where numerical factors such as h bar over 2 and like 1/2 is dropped. And the reason is that we don't necessarily care exactly how delta y is defined. Sometimes delta y is defined as the standard deviation of the wave function, or some other thing like you can define delta y as the full width half maximum. Depending on how you define these quantities exactly, there may be some other numerical factors which appear, and we're not actually interested in those numerical factors. We want the physics up to a certain numerical factors which can be worked out later on if necessary. So here, let's ask the question now. What is the uncertainty of a photon in this beam along the y direction? So we don't exactly know how to define it precisely, but we know that that's on the order of the value value d, right? So the length scale parameter is only d. So it could be, half d or maybe pi d over 2 or something like that. Pi d over 2, that's actually a little bit too big. Anyway, so d over pi or something like that. Depending on the definition, the exact value of delta y will be different, but up to a numerical factor, we know it to be surely d. So that's the kind of calculation that we're doing. So what that means is then we learn something very important. Delta py is this. So that's the lesson from Heisenberg uncertainty principle. Let's stop and think about it. If you didn't know the Heisenberg uncertainty principle, then you might think that, well, this is just a cylindrical beam. It looks like all the light is going to the right, and that is true on average, right? That is true on average. So what that means is that if you think like that, if you just take that average behavior as the true behavior, then you might think, oh, this beam will just go on forever as a perfectly cylindrical beam. What the Heisenberg uncertainty principle says is the following. Even though it looks like the beam is going to the right, and there is no beam going to the y direction, nevertheless, there are fluctuations here which give some uncertainty in the y momentum. So some photons are actually going to the right and up a little bit, and some photons are going to the to be sure, there are some photons that are going straight to the right, and then there's some photons going to the right and up, and then there are some photons going to the right and down, and so on and so forth. So and the same photon will actually also go through these fluctuations in the course of the motion. So that's it. So these fluctuating values of y momentum gives rise to this delta y, delta py, according to quantum mechanics. So then, how do we actually characterize this delta py? Remember that this is a monochromatic light, so that means k or lambda or omega are fixed. Well, that's related to energy time uncertainty principle. We're not going to consider that at this point. So let's say that the photons have a definite k. If it has a definite k, and if the direction can be fluctuating like that, then you can say the angular uncertainty can be related to the delta py value as follows. So this is the k, which is given by 2 pi over lambda. Lambda is a frequency, and according to this diagram, xy plane is the cross-sectional plane. So that means this is the z plane, z-axis, and this is the y-axis, and so that means ky. The wave vector component along the y direction is 2 pi over lambda times sine theta. So if this theta is the sort of the angular uncertainty of the beam, then this ky, what we wrote down here, h bar ky here, is basically delta py. So that's the connection between the angular uncertainty of this beam to the momentum uncertainty of this beam along the y direction. So then, what do we get? Let's take this formula here, and let's actually take these other two here, and let's make use of them. Let's combine these. But when I do that, I'm going to actually use delta py I'm going to drop 2 pi here, because there's a lot of room that these expressions are wrong in terms of the exact numerical factor. All I'm saying is that delta y is the scales of delta y, scales of delta py, and so on and so forth. So delta py is basically this h bar times that. So I'm ignoring 2 pi. That becomes h bar over lambda sine theta. And so that is greater than or equal to h bar over d. Guess what that implies? You can see it, can't you? So you can see that this can be summarized as d sine theta greater than or equal to lambda. Ha ha ha. We saw that d sine theta being on the order of lambda, that's the diffraction condition. Well, we derived the same condition from Heisenberg uncertainty principle, and that's the quantum mechanical view of diffraction physics, and that's how angular uncertainty is associated with the Heisenberg uncertainty principle along the y direction. And of course, this y direction is not special. You can take x direction or any direction in the plane of the cross section of the beam. So, and the beam will spread in all directions, because even though it may not look like this beam has y momentum values, it actually does. So over a long period of time, it will actually spread in the y direction, x direction, in all the directions. That's why you get blurred beam.